So some of you probably got pretty large errors, at least for some of the trials of your project with the carts and the hanging weights, especially if the hanging weight was pretty small. But we can actually adjust for those errors. So that's what I'm going to show you right now. Okay, so you can see I have the cart. It's attached to the string. String goes down to the weight. And right now, I've got 10 grams on top of the 5-gram hanger, so a total of 15 grams there. What I'm going to do is pull the cart back until the hanger is just on the ground. So basically, also, when the string is just barely tight, and I'm going to record that position of the cart. So it looks like it's pretty much right on 48. Okay, so you probably figured out in the lab that a way you can measure the height that the mass goes up is the same as the distance you pull back the cart. So if I take the cart to 98 centimeters, the hook with the weights are it's now 50 centimeters in the air, and I can let this go, and it'll keep going. There we go. Whee. Okay. So there was an interval where the cart was still going, but the weight was already on the ground, and that point is 48 centimeters. So for this continued motion right here, there's no change in gravitational potential due to the falling weight. Now, in the lab, we basically assumed that there would be zero acceleration during this last component, right? That would also be assuming that friction is zero, or the track is perfectly level, or any other features that would cause an external force on the cart. And if you had a pretty big percent error, and your calculations and data were right and everything, that would probably be due to similar losses of energy during that part where it's still speeding up. So that loss of mechanical energy, remember mechanical is potential of the hanger, there we go, potential of the hanger as well as the kinetic energy of both the hanger and the cart. We can lose kinetic energy if there's work being done on the system. So I'm going to write out the equations and show you what I'm aiming at. Okay, so let's set up 3 states. So in state 1, there's the floor, here's the table. In state 1, the cart is back here and the weight is hanging. We are going to call that x naught. The second state, so this is state 0. In state 1, we have the cart is still moving, so we have a velocity v1, but the weight is now on the floor. Ignore the fact that my lines aren't adding up to the same length. Okay, and then we have the final state where the weight is still on the floor, but the cart has reached almost the very end. So there's still a little bit of a velocity, but it's not as big as the velocity in state 1. And of course, the velocity in state 0 is 0. Okay, so we're going to have, remember our guiding equation is delta E equals W. So the energy of state 1 minus the energy of state 2 is going to be equal to the work between states 0 and 1. I think I said state 2. Energy of state 1 minus energy of state 0 is equal to the work done between states 0 and 1. we had basically assumed that this was 0. And that's what we're going to correct. So first, we see that the energy of state 0 is just the gravitational potential, so UG0. And so that's state 0. And then state 1, the potential is now 0, so UG1 is equal to 0. So the energy is just equal to the kinetic energy at state 1. And put those together, that's going to be equal to the work. Now, that work is going to be done over the distance that the cart travels there. So if we call this x1, and this is going to be our final state x2. So x1 is the 48 centimeters that I showed you, the position of the cart when the weight had just touched the ground. I'm just going to check that this is still recording. Okay. This is my second time recording this. And then this is going to be that 98 centimeters that I showed you. And I didn't show you x2, but that is going to be the position of the cart right when it touches the end of the track. So there's that barrier at the end of the track, and right when the cart touches that is at 8 centimeters. Obviously, I need to convert all of these to meters, but that's our starting point. We also have the mass of the hanging weight is 20 grams. This is going to be 0.02 kilograms. And the mass of the cart is about 1/4 kilogram. And all we need then is to actually measure these velocities. We can get the height as being just the difference between x1 and x naught. So our equation is going to be 1/2 all the mass that is moving, so m plus big M, times the speed it's going at state 1, v1 squared, minus the height that the cart was, so the height that the hanger was, which is the difference between those. So we've got the mass of just the thing that's changing heights, times g, times the height. So that's going to be our x naught minus x1. Now, for the work, remember the equation for work is FD cosine theta. And so this is going to be the force due to any external forces, whether we know them or not. So probably friction's involved, probably the horizontal component of gravity if the track is not perfectly level. Those might both be factors. But we don't need to specify. We just need to know that there's some external force doing work. And the distance that it travels is x naught minus x1. Now, again, we had assumed that this is equal to 0. With this procedure that I'm showing you right now, we are going to calculate this so we can see if the whole energy equation matches up. And so the way we'll do this is the percent error. We're going to write it slightly differently than what we had in class. So we're going to count the initial as UG, and we're going to calculate the final as K1 plus W01. I guess minus with the signs that I'm using here. And so our error is going to be final minus initial over initial. So that's going to be K1 minus WO1. Now remember, this work is going to be negative because it's taking away energy. So we're going to be subtracting a negative number here. And we're going to subtract our UG naught and then divide by UG naught. But we have to figure out what this work is. And so to do that, we're going to look at the change in state from 1 to 2. So again, delta E is equal to W. But this time, we're doing E2 minus E1 is equal to W12. If we look at state 2, all we have is kinetic energy. In state 1, we've already found we only have kinetic energy. So this difference is 1/2 the mass of everything that's moving, so m plus m, v2 squared minus the same stuff, but v1 squared, the same equation as we had above. And that is going to be equal to this external force times the distance that it's moved between those two states. Well, that distance is the difference of x1 minus x2. Okay. This doesn't matter very much. Normally, we think of the f that goes into this equation as being a positive number. I've just written it so that the external force is also going to be negative compared to the motion of the cart. I think that'll be less confusing that way. Okay, so now we're going to actually collect the data because what we need is V2 and V1. V1 is the data that you actually collected already, and V2 is the extra information we need in order to actually answer this question. Okay, so we are going to measure the data with SPARKVUE just like you did in class. And so remember, we're looking at the data at 3 points in time. I'm going to start the cart at its 98 centimeters, and I'm going to let it go, passes, and then it ends. So if we look at the data here, this is the portion where it's speeding up and going down the track because of the falling weight, right? This point, so I'm aiming for the very highest point here, this is when it reaches its highest speed, and this is due to the weight having pulled it. The weight hits the floor, the weight is no longer pulling it. And we still have an interval of time, though, before the cart hits the end of the track. So this right there is state 1, and over here is state 2. So I'm going to try to remember these numbers well enough to take it back to the page we're writing. So we've got 690 and 666. So V1 was 0.690 meters per second, and V2 is 0.666 meters per second. Totally reasonable number. Okay, so I'm about to leave it where you can finish. So what you'll do is to use these values and the values that we had up here in order to calculate all of this, and then finally divide by x1 minus x2 to get a number for the external force. So this will be something other newtons, and it'll be negative because of the way we set up our equations. Then you're going to take this number and you're going to plug it into the E1 minus E naught is equal to WO1 equation. So this was K1 minus UG naught. And we wrote equations for that above, times Fx is equal to fx times x1 minus x naught. Now we know these, and we know this now from what we just solved. We already knew this. You did this when you were doing the lab originally. And what we're going to end up with is this value that we can compare right here and get the percent error. The original if we are ignoring work, would have been K1 minus UG naught over UG naught. And that would indicate whether we lost some mechanical energy going from state 0 to state 1. This is the error, or at least a way to calculate the error, that a lot of people were getting pretty big numbers, maybe hopefully not more than 30%, but I know some people did. But if you do this work correction, as we outlined here, hopefully we'll get it down to like 5% or at least 10% or less error. And I'm talking about the magnitude. Even though I'm not going to put absolute values around this, these are probably going to end up being negative because probably there was ultimately some energy lost. And I'll go ahead and put the times 100%. I hate even writing this down because 100% just already literally means that. And I get a phone call right when I was ending. Okay, that's it.